Okay, this video lecture is over Chapter 4 of your textbook, and it is titled Packet Capture and Analysis. So, first, what is packet capture? You've probably been exposed to this if you've taken any of the Cisco classes, possibly in CIT 111 if you had that, but it is the capturing and possibly storing of network traffic. And this is one of the most important skills for investigation that involve network traffic. That is, somebody's connected to your machine, or you have a botnet running, or something like that. So some sample tools are the most common, Wireshark, which you have already had an assignment for and may or may not be familiar with from other classes. And then we use TCP dump, which is a command line version of a packet capture, came from the Unix world, and then somebody ported it to WinDump on a Windows machine. And like I said, you should have already had a homework where you've experimented with those. Another command we'll be talking about and using is tshark. And tshark is a command line version of Wireshark. And then at some point we will probably experiment with Snort. In addition to packet capture, it's an IDS/IPS. IDS is an intrusion detection system, and an IPS is an intrusion protection system. So in an IDS, it detects that something may be going on that's not appropriate or good, and it will alert you somehow. It'll, pop something up on the screen, it'll send you email, it'll text message you, whatever you set up. An intrusion protection system detects and fixes the problem. So it proactively applies firewall rules, kills processes, whatever is appropriate to deal with the attack that Snort identified. Even though it's referred to as packet capture, what we're really catching is frames. And because it involves dealing with the network stack, that is to see packets, you may need administrative access to use these commands and actually get information. And if we're capturing packets that are traveling on the network that are not destined for our machine, that software is said to be running in promiscuous mode. TCP dump and tshark, as I just mentioned, are command line capture tools. An example of TCP dump is this. We run the TCP dump command, and then I want to capture, the -C is really for count. I want to capture 3 packets. Now notice the first time I issued the command, I was on my Wayne account, which is a user account, and it told me that I couldn't get access to the network stack and or ports to do that. So then I SU'd, which is substitute user, but SU with no arguments will SU to root. Once I log in, I'm logged in as root, which is the administrative account on Unix machines. I issue the exact same command again, and now notice I do get capture and information on 3 packets. And then it gives me some statistics. So that's TCP dump. Now, as far as tshark, very similar. I said tshark-count 5. I'm on my laptop, so I don't have a hardwired connection. I'm using Wi-Fi. And then it shows me source and destination IP addresses, what type of traffic it is, and what ports it's traveling between, and how much data is in each of the packets. So slightly different format, but gives you very similar information as TCP dump. Now, sometimes it is necessary to use something called a tap. And what a tap does is it connects to the network and it inspects traffic to determine where the packet needs to go. So there are less traffic with a switch. So in a switched network, a lot of times you can't see all the traffic. And that is the disadvantage. Not all packets on a network. So the sniffer may not see all the packets if you're in a switched environment, which is kind of the modern type of environment to be in. So one solution to that is taps. And I'm going to go back in time about 30 plus years when we had ThinNet and ThickNet Ethernet. So here is going to be an image of a ThickNet cable with a tap. And that ThickNet cable, that orange cable, is 9.5 millimeters in diameter. So it's a pretty good size cable. And that cable, based on the wavelength of the signal traveling, has little plus or X signs as to where you can tap. So you drill a hole just right to the center conductor, and then you clamp this tap onto it, and then the cable out to the left is a data communications cable that is going to your sniffer or your computer. So a modern tap looks more like this. So we can plug two networks in, and then any traffic on either the network or traffic traveling between the networks will go out that monitor port. We have a USB style and an Ethernet style monitor port so that you can see the network on there. That's one solution. A better solution, if you have a capable switch and you have administrative access to that switch, is to use port spanning, which is an alternative to taps. This is usually only available on larger switches, which translates into more expensive switches. And what you do is you configure the switch to copy traffic from one or more ports to a monitoring port. So that's one way to solve that problem if you can't see all the traffic. Now, talking about communications address, this is just kind of a tangent. It's something you should already know. It is something I harp on, which means you will see it on homeworks, quizzes, and exams, almost guaranteed. And that is, if you are communicating between two devices that are on the same network, you use a MAC address. MAC address stands for Media Access Control. Now, if you're communicating between two devices that are not on the same network, then that communications happens using the IP address. And IP stands for Internet Protocol. So when I ask you what address is used to communicate on layer 2, your answer is simply MAC or MAC address. Don't try to elaborate. Don't say MAC and IP address, because ultimately it is just the MAC address. Likewise, if I ask you about hosts that are not on the same network communicating, then your answer should be IP or IP address. Now then, there's this protocol called ARP. It's a layer 2 protocol, which is the data link layer, and it stands for Address Resolution Protocol. And the purpose of ARP is to provide the MAC address of the device on the local network that has a given IP. So what happens is a device has an IP address that it wants to communicate, and it broadcasts a message to all the hosts on the network and says, who has this IP? Now, if the host is on the same network, it'll respond back, that's me, here's my MAC address. And then that MAC address can be used to communicate with the device. Now, if it sends out who has this address and it is not a device on the local network, then the default gateway or default router, whatever you prefer calling it, will respond and basically say, that's me. But in reality, it's saying, if you communicate with me, if you send the frame to me, I'll send it on to its next hop so that it will make it to its final destination. And that's what I say here, that if it's on another remote network, the default router will respond with its MAC address. Now, one common attack that we have involves ARP, and it's referred to as ARP spoofing or ARP poisoning. And basically what an ARP spoofing attack is it's an attack in which a device or software tries to respond to ARP requests before the real correct device replies. If it is able to do that, that will cause the packet for which the ARP request was made to go to the device other than the intended device. So you can try to redirect, capture, or view traffic that is not destined for the machine that is doing the ARP poisoning. Now, we have something called a gratuitous ARP, which is just when a system says, hey, if anybody cares, here's my MAC address, trying to get it cached so if somebody wants to communicate with it, the process is a little quicker. Gratuitous ARP can cause a problem because when you do it, some machines will blindly put that information in their ARP cache. So, they don't have to try to beat the ARP request. They've already done that by poisoning the ARP table. Now, when I was doing this, I was going to see how easy it was to do. So I wrote a short Python script, which is a 41-line program, but in reality it's probably more like 15 or 20. Because I put blank lines in to space it out and make it look nice. I put comments in. And kind of the heart of the program is this ether command where I basically send a ARP packet out an interface with the send packet or the send p command, and was able to do ARP poisoning. Now, I first tried to poison the ARP on my machine, which is a Mac OS machine, and Mac OS has some things built in to try to prevent this. So it's like, get serious, you're on this machine, I know you're not giving me valid information. So when that happened, I fired up my daughter's Mac and ran the program, and instantly that ARP entry appeared on her machine. So it's pretty easy to program and carry out ARP spoofing or ARP poisoning. The next thing the book talks about is passive scanning. And that's where we're watching for packets on the network and looking for particular information, like certain types of packets or packets with certain contents in them. So that's what passive scanning is. Now, this led me to do a little sidebar or go off on a tangent, which is the Unix find command. And it searches the file systems for file system objects based on certain criteria. Now, I knew I'd written a Perl program that I wanted to get some information from and possibly rewrite it in Python, and I could not find it easily. It was not where I thought it should be on my laptop. So what I did was I ran the find command. And the find command basically says, going down, find, starting at the current directory, that's what the dot is, any file name, I don't care what it is as long as it ends in .pl, and print the path out. Now, find is real handy if you know that you have some type of vulnerability and know that the file is always stored in ABC. but you want to know if that exists on your system, you can use the find command. So I'm pretty confident in the relatively near future I will write a whole lecture on the Unix find command because it's that handy. Now then, the Perl program that I was looking for was an example of a program that I wrote to do passive scanning. And here is kind of the most important part of Perl. And Perl is kind of the predecessor to Python. So syntax is a little different, but they're very similar. So what I did is I gave the path /user/sbin/tcpdump to the dump command. As far as options, I wanted to use interface EN1. And then what I do is I open that command, and notice I have a pipe on the end of the command, and then I open a data file. So what that's going to do is it's going to run the TCP dump command, and it's going to feed that into my, in this case, Perl program for processing. Now what I did is I went through and I looked at host names or IP addresses that I saw, and I said if I don't have that in my associative array called host, associative arrays were converted into dictionaries, but they're the same kind of data structure in Python and Perl. And what I did is if I didn't find that host, I would add it to my associative array and set the count of the number of times I've seen that machine to 1. Otherwise, that is already in my table. I have seen that host before, so I'm just going to increment the host count for that particular host. So that was an example of something I did. I don't remember exactly why I did it, but allowed me to give you an example, a real world example of passive scanning. Another passive scanner is P0F. When I was playing around with that, I haven't used that before. So on my machine, I said brew install P0F, and it installed it, and it ran fine. You can look over listing 4.6 of your textbook for an example of running this command and what the output will look like. Now then, when you use Wireshark to do packet capture, often your desire and investigation is to do the packet decoding. And what decoding means is I'm going to take the raw packet, really the raw frame, and I'm going to break it into its pieces, and I'm going to display information in an easy to read format. Figure 4.5 of your textbook looks like this. So notice down at the bottom left you have the hexadecimal equivalent of each byte, and notice the second line starts with 10, so that is 10 hex. So the first line contains 16 packets. 16 bytes, byte 0 through byte 15. This line starts with 16 and goes to 31, etc. Now over on the bottom right, where a lot of those dots are, is it will take these characters and convert them into their ASCII character, displaying that character if there is a match, otherwise just putting a period there. So if somebody sent a password in clear text, it might be visible. If the protocol like FTP is using ASCII text to talk to the FTP server, you might see things like what's your user ID, what's your password, and what the user types in if it's not encrypted. Now up in the top main window, notice that it starts at the frame level. So level 2, I got 102 bytes. Ethernet, if I decode that, it's going to tell me layer 3 information. I'm sorry, layer 2 information. Notice it has MAC addresses. It's actually decoded the OUI, which you might look up if you don't know what that is. Then at the next layer, the network layer, we have IP information. We have the destination. This is using TCP packets going to port 80. Port 80 is Hypertext Transfer Protocol. And the response that I have is I have some text that is HTML text. So all these little arrows or triangles to the left of these, if you click on them, will decode the particular level of the packet that it is examining. So really, really, really handy thing. Now, on a busy network, you're going to get a lot of crap, not necessarily what you're looking for. And if that's a problem, you can use Wireshark filtering. And basically what filtering is saying what packets you want to see or possibly don't want to see. So in the Wireshark top left, you have a bunch of icons. In my case, the blue fin is start capture, the red square is stop capture. But below that, you have a display filter. And you can type certain things in there. I'm going to give you some examples. If you type in HTTP, this is only going to show you HTTP protocol packets. So notice how there are big skips in the numbers to the left. So it's filtered out, 9,000 packets before it shows me the first HTTP response. It's showing me the gets and the responses. It's telling me the source and destination. And of course, because I said only show me HTTP, under the protocol column, the only thing we see is HTTP. Now then, we talked about ARP. If you want to show all the ARP packets, you just simply type in ARP, and it will do that. If you only want to see packets going to or from a specific host, you can say IP.address equals, and then the IP address of the machine. Now, if you just say IP.address, it'll be packets coming to or leaving the specified machine. If you want to know packets coming from a particular machine, you can use IP.sourcehost. And same IP address, but this time it will only show packets that are leaving that machine. That machine is the source of the packet. You can do things like http.request.method equals post. So it will only show me post request. It will not show me get request related to the HTTP protocol. So there are a lot of handy things you can do, and you can build very complex filters based on whatever you're trying to accomplish. Now, the book talks about Wireshark statistics, which is sometimes useful when you're investigating a network. There are a lot of statistics views you can get. I think there's like 12 to 20. But if you look at figure 4.9 or look in Wireshark, you will see those statistics. There's another view that I like a lot called the protocol view, and it looks like this. 100% of the things I captured were frames. 100% of those frames were Ethernet. 46.5% of them were IP version 6. 52.7 of them down at the bottom were IP version 4. And it just tells me information about the packets and what percentage of the packets, and then it actually tells me how many packets there were, and then over at the far right, how many bytes those different protocols used. The next thing the book talks about is following streams, and that's viewing packets associated with a stream, which is recreating a conversation from captured packets. So to view a stream, you can right-click on one of the packets that's being displayed in Wireshark, and then you can apply as filter the selected packet, and it will go through and reconstruct the conversation for you. The next thing your book talks about is what they call gathering files. And basically what that is extracting files from a capture file. So if you have a conversation that went on that was transferring images or HTML documents, you may be able to extract the useful information out of the conversation or out of the stream and recreate that file. So I will have you do that on Homeworks because it is a very handy thing. What you do is you go to the File menu in Wireshark and choose Export Objects. And then what happens is you then select the files that you want Wireshark to look for. And then you can select objects that are of that particular type and then store them to the local machine. The next thing that the textbook talks about is a network miner. And network miner is software from the company NetResec that examines network packet traffic and tries to determine, quote, bad things that are going on. Unfortunately, this is Windows only, but it's still important to know of its existence. So with that finishes up the lecture on Chapter 4 of your textbook.